Hello everyone, this is Arnold Rangakuramia from Kisembo Academy, helping you manifest academic excellence, and in today's video, we'll be exploring the following. In this video, we'll discuss the law of electrostatics, insulators and conductors, the concept of the proof plane, and precautions we ought to take when carrying out electrostatic experiments. We'll also discuss corona discharge, and we'll see how corona discharge is applied in a lightning conductor, and eventually we will discuss about electric fields. First, we'll look at the law of electrostatics. It's as simple as that. It states that like charges repel and unlike charges attract. It means that if you have a positive charge and a positive charge, when you try to bring them together, they'll repel. Or if you have a negative charge and a negative charge, you try to bring them together, they'll repel. They'll resist to come together. But if you have a positive charge and a negative charge, when you bring them close, they'll attract each other. It is that simple. It is the same law that we use even with magnetism. So what are insulators? Insulators are simply materials that can't conduct electricity. And conductors are the reverse. These are materials which allow the flow of heat and electricity, and these insulators do not have free moving electrons. That's why they won't be able to conduct electricity or heat. Conductors have free moving electrons, and it is these electrons that are free moving that help in the conduction of electricity. What is a proof plane? This is simply a small metallic disc. A small metallic disc that is mounted on an insulating handle, and it is used to collect charges from conducting surfaces of different shapes. Now, how exactly does this work? Now, when we put this proof plane, the metallic disc of a proof plane, in contact with a conducting surface of interest, the plane is then transferred onto an electroscope, which serves to show the magnitude of the charge by the deflection of the gold leaf. Therefore, this serves to show that a proof plane is used to tell the amount of charge at a point on a conducting surface. If we look at our diagrams here, we have a conductor here that is in that shape. We have a proof plane, and these are several proof planes being put on different points on that conductor. Now, from my earlier explanation, I just told you that you simply bring this proof plane, the proof plane, put it on the surface of this conductor, remove it, place it on the cap of a gold leaf electroscope, look at the deflection, and you're able to tell the magnitude of the charge. But if you look at this conductor here, we can say it is positively charged. But the positive charges, when you reach at this sharp point, there are more positive charges, they are more congested. It means that the charge density here is high, and when you go to these areas that are a bit flat, you see that there are less positive charges. It means that the charge density along these flat areas is low. But as you're coming towards the points, the charge density is high. There are more positive charges that are congested there. So you realize from this illustration that at sharp points, the charge density is high and it is low along places that are a bit flat, or they are not exactly sharp. So this brings us to the next definition that we need to talk about. What exactly is surface charge density? Surface charge density is simply the amount of charge per unit area of the surface of the conductor. And because of very high surface density, it brings us to the action of sharp points. The action of sharp points is as a result of very high surface charge density. At sharp points, there is a very high charge density. This leads to high electric field around the sharp points, which ionizes the air molecules at the sharp points. This is the sharp point we are talking about. And now, because there is a very high surface charge density there, this is going to ionize the airs around here. And when the air around here is ionized, that is what we are calling the action of sharp points. Now, when a sharp pointed conductor like this one causes ionization of the air molecules around it, the ions that are opposite this charge, in this case they will be negative, the ions that are opposite this charge or that are opposite the sharp points will be attracted towards the sharp point. Now, when they are attracted towards the sharp point, they neutralize this sharp point. Now, of course, when they neutralize this sharp point, it means that this sharp point is losing charge, right? Yes. So now, this apparent loss of charge by the conductor is what we call corona discharge. I'll say that again. When a sharp-pointed conductor causes ionization of the air molecules around it, ions that are opposite are attracted towards the sharp point, and those ions neutralize it. So this apparent loss of charge by the conductor is what we call corona discharge. So let's look at the precautions that we take when carrying out electrostatic experiments. When we are carrying out electrostatic experiments, fire should be kept away from the apparatus, since fire produces ions which can discharge the bodies. Also, experiments ought to be carried out in dry environments, because damp environments have moisture which carries ions that can discharge the bodies. Up next, we'll look at the application of corona discharge, and in particular, we'll discuss how a lightning conductor works. We have all experienced lightning and thunder. Lightning comes first, then thunder is heard later, since light travels faster than sound. I'm sure we've all heard, probably over the news or physically, how lightning sometimes destroys buildings and trees, sometimes causing death to people that especially take shelter under the trees when it is raining. To protect a building from the disasters caused by lightning, a device called a lightning conductor or a lightning rod is normally placed at the highest point of a building. This device was invented by an early scientist called Benjamin Franklin, the very reason why it is sometimes referred to as the Franklin rod. In this tutorial, we shall discuss how this lightning conductor or how this lightning rod works. It's Kisembo Academy, and thanks for tuning in. First, we need to ask ourselves, how does lightning occur? Now, during a storm, the clouds move fast, and as a result, rub against each other and against air. This rubbing makes them to acquire charge. This charge is normally distributed on a cloud in such a way that the top part is positively charged and the bottom part is negatively charged. Lightning occurs when a certain electrostatic discharge occurs between two electrically charged regions of the cloud, or between charged clouds, or between a cloud and the ground. In other words, when two oppositely charged clouds get to be near each other, a huge spark of electrons jumps from the negatively charged cloud to the positively charged cloud. It can happen between two clouds. It can happen within a cloud, because this part is positive and that's negative, so the spark happens between the cloud, or it can happen between the cloud and the ground. This spark generates a lot of heat, which warms up the air around, causing it to rise. When the air rises, air from the neighboring layers reaches to the spot to replace the risen air, and in so doing, a loud sound is produced. This loud sound is what we call thunder. So now, when all this happens, how does the lightning conductor work? Here we have a lightning conductor, a schematic diagram. In this diagram, we are having copper spikes that are connected to a copper strip, and this copper strip at the bottom is a copper plate. It is more so like this. This is a lightning conductor with the copper spikes. It is connected to a copper rod which goes along the building, and it is buried into the ground. So what exactly happens here? How does the lightning conductor work? These are the spikes. When a negatively charged cloud comes near the spikes, a very high positive charge is induced at the spikes. This creates a very high electric field around the spikes. Now, the very high electric field around the spikes, it causes the ionization of air around the spikes. So when the air around the spikes gets ionized, you're going to have positive ions in the air will be repelled towards the cloud, and in so doing they will be discharging the cloud. The negative electrons are attracted to the spikes. As a result, the electrons from the cloud are safely conducted to the ground, and this prevents lightning from striking the building. The electric field. What exactly is an electric field? It is simply a region around an electric charge where an electric force can be experienced. And as you can see, an electric field is always represented by lines of force. Now, these lines of force have got a direction, and by definition, the direction of an electric field at a point is simply the direction in which a small positive charge would move under the influence of the field if it was placed at that point. So it means that if this is a positive charge and we placed a small positive charge, if this is positively charged, and we placed a small positive charge here, it will move in that direction, because we said like poles repel, and then like charges repel, and unlike charges attract. So if this is a positive one and that's a positive charge, like a positive charge placed here will move in that direction. It will move away from the positive charge. But if we put that positive charge here, and this is negatively charged, that positive charge will move in that direction. And that is how we defined our direction of field. So the direction of field will always move away from the positive and towards the negative. These directions, or these electric fields, have got lines of force. The arrows on the lines of force show directions of the force on a positive charge, and the force on a negative charge will always move in the opposite direction. So here we have like charges, a positive and a positive. They are having the same kinds of electric fields, and because from the law of electrostatics, like charges repel, and as a result we have point X, which we are calling the neutral point, and at that point the electronic field strength at that point is, the resultant force at that point is 0. Unlike charges will attract, and because they do attract, their field lines merge as seen. This is a positive and that's a negative. We also have illustrations for lines of force for two plates, electric plates. This plate is positively charged and that is negatively charged. The lines of force will move from the positive towards the negative. The electric field lines will be such that they will move from the positive plate to the point charge, which is negative, as illustrated in the diagram. This brings us to the end of this video. Please don't forget to comment below or hit that like button. Someone out there might like to watch this tutorial. Don't forget to share. Otherwise, for more videos, simply subscribe to this channel. For Kisembo Academy, this is Arnold Rangakuran.